Of RRS Live. My name is Gideon Lombardo, and I'm a junior in the Randall Research Scholars Program studying aerospace engineering. Today, I will be presenting my project titled Enabling the Autonomous Flight of Crazyfly 2.1 Quadcopters, conducted under the supervision of Dr. Christian Cousin in the Control of Human and Robotic Systems Laboratory. In this presentation, I will introduce the basics of my project in the context of its real-world applications. To effectively explore the project, we will have a brief introduction into control theory. Afterwards, I will talk about the crazy swarm architecture which we use to fly our quadcopters. I will then show milestone flights that we have achieved in the lab and detail the future directions of our work. Our lab is focused on control systems, meaning we want to control the objects in our surroundings. We believe that our research has immediate impact in today's society with the growth of autonomous systems and the demand for automated innovation. In the case of this project, we want to automate the flight of microdrones. The microdrones we use are Crazyfly 2.1 quadcopters developed by a company called BitCraze. These drones have applications in the modeling of autonomous delivery systems and the modeling of other VTOL or vertical takeoff and landing vehicles. Integration with other robotic systems will allow for the modeling of real-world robot-to-robot interactions. To visualize this, imagine a cargo truck driving down the highway with an accompanying fleet of delivery drones. The delivery drones will take packages from the truck and drop them at the consumer's doorstep, and then redock to the truck to receive new cargo and fly them to the next consumer's house. A system like this is something we could model using the setup in our lab. So we've talked about why we want to use controls, but let's talk a little bit more about what controls are. When it comes to controls, we can have two different types. The first is open-loop control. Open-loop control does not make use of any sort of feedback mechanism and is an ineffective control design. Closed-loop control does make use of some sort of feedback mechanism. We can then make linear and nonlinear distinctions when we talk about controllers, and this refers to how you're mathematically modeling and approximating your system. Linear approximations are great and are used in various engineering applications. However, sometimes they break down. For example, the small angle approximation. When the sine of theta is approximated as theta, that only works for a certain set of angles. If the angle is too large, that approximation no longer works. It's the same kind of thing when we're talking about controls. So we want to focus on closed-loop, nonlinear controls in our lab. Further exploring the closed-loop model, we have our reference. Our reference is what we want our system to do. In our case, this is a desired trajectory or some waypoint for our quadcopter to visit. This gets sent to the controller, which then tells the motor to spin. This will then generate the dynamic that we specified, whether that's a stable hover, a waypoint to visit, or some sort of complicated trajectory. We can then use a sensor to measure the actual position of the quadcopter. Once this is done, we can then calculate the error, and the error is defined as the difference between our desired position and our actual position. Based on the error, the controller will be able to issue a corrective command to the quadcopter so that we can achieve our desired flight. One of the largest challenges that I have encountered during this project is implementing a system that is able to automate the quadcopter flight. We've decided to use the Crazy Swarm system, which is an architecture developed by a lab at the University of Southern California using a setup very similar to our own. This is a repository that is offered on GitHub, and you can see the link here on the slides. This system uses languages such as Python and C++, and also uses ROS, or Robot Operating System, to command the quadcopters. This gives us real-time and simulation capabilities, and it allows a motion capture system to track the position of the quadcopters, and then uses the IMU, or Inertial Measurement Unit, on the quadcopters themselves to track the rotation. Given this data, the controller designed for the Crazy Swarm system will be able to issue commands to the quadcopter via a crazy radio antenna. The diagram that you see here on the slide should give you an idea of just how complicated this architecture is and how many different pieces there are. In our lab, we use Vicon 2.2 cameras and the accompanying motion tracking software Vicon Tracker to track the position of our quads. The data is transferred from the Vicon cameras to the computer which houses the Vicon software, and then over an Ethernet cable to the computer which houses the Crazy Swarm architecture. The computer which houses the Crazy Swarm architecture has a USB radio antenna plugged into it, which issues radio commands to the quadcopter, closing that communication loop that you see in the diagram. Our lab uses unique marker configurations so that the Vicon system can identify each quadcopter individually. These unique marker configurations correspond to an ID number given in the Crazy Swarm system so that the Crazy Swarm system can ID each quadcopter individually. It is also important that we have each quadcopter set to a specified radio channel so that we can ensure the most effective kind of communication in our lab. To generate custom trajectories, the creators of Crazy Swarm offer a second repository on GitHub. This architecture works by reading in a CSV file that might have XYZ waypoints and then computing a polynomial trajectory and then writing a new output file which the Crazy Swarm system can interpret. It is also possible to write a Python script using time position pairs to generate a CSV file which can then be put into the trajectory generation script to create the Crazy Swarm adaptable CSV output. So what you see here is a spiral that I generated using the time position pairs. So you can see the 3D motion here on the top graph. It is just a singular rung of a spiral. And then under that, you see the velocity, acceleration, angular velocity, and yaw angles, which are also important parameters of the flight. I then exported this to the Crazy Swarm architecture and was able to fly the drone. So now it's time to take a look at some of the milestone flights that we have achieved in the lab. The first one we would like to take a look at, and the most important one arguably, is the stable hover and land. So here the quadcopter receives the command to take off and reach its desired height. It then will hover in a stable manner, and then it will receive the command to land and land safely. The next milestone we want to look at came from hovering two quadcopters at the same time. So the quadcopters will receive the command to lift off and they will reach the same desired height and hover stably. This would not have been possible without the work of Eric Wang, a student who worked in our lab this summer. To demonstrate the power of our system, we would like to take a look at some more complicated trajectories. The figure 8 trajectory is the most complicated trajectory provided by the Crazy Swarm authors. Here the quadcopter receives the command to take off and reach its desired height. Once this happens, it will go through a figure 8 trajectory, creating one big loop, passing through the center point to create another big loop. Once it reaches back to the center point, it will reverse its trajectory, creating a figure 8 in the opposite direction, as you can see here. It will then reach the center point once more and receive the command to safely land. I would now like to take a look at the spiral trajectory that I showed earlier. This is the trajectory that I implemented myself. The quadcopter receives the command to lift to its desired height, as we've seen in all of the other ones, and then it will slowly move in a spiral fashion up to a single rung of the spiral. Once it reaches the apex of its flight, it will then reverse its trajectory, like we saw with the figure 8, and descend on the same path that it came up, as you can see it doing now. Once it reaches the bottom of the spiral trajectory, it will again receive the command to land, as you can see here. Looking forward, I will continue to generate complicated trajectories to test the limits of our system. We also want to investigate more swarm flights, and this just means flights with more than one quadcopter. To do this, we'll have to investigate things such as collision avoidance, so our quadcopters do not run into each other. Once this is done, we will be able to design our own controllers for the quadcopters, and this will allow us to model the real-world systems that we saw earlier in the presentation. Thank you all for your time. Does anyone have any questions?
You mentioned in the swarm, you want to have collision avoidance for multiple copters. There's also a concept called hard real time, where there's different scheduling. Each copter would have to complete certain tasks in a fixed time, or else the whole mission's gone. Does Crazy Swarm or anything you looked at support hard real time constraints, or is the collision detection and those things done in some other manner?
So the collision detection is done as part of the Crazy Swarm platform. It does take in like an additional configuration step. But the great thing about Crazy Swarm is how adaptable it is. It's designed to be very, I don't want to say plug and play, but very buildable so that you can add your own kind of parameters to it. So that's something that we could definitely look at, but Crazy Swarm has not defined it itself.
So with your feedback methods, how are you balancing, say, the Vicon system and potentially any other things housed on the drone itself, like an IMU, anything like that?
So that's kind of all done in the Crazy Swarm software itself. That's not something that we can change unless we kind of look into the hardware of the quadcopters themselves. The rotation data can be used from the Vicon system, but it's not as reliable as from the IMU. So those specifications were made by the authors, and we can change them when we want to, if we want to. But as we're just trying to validate the system, we haven't really looked at that yet.
So what do you think are the specifications or limitations of the Crazy Fly quadcopters?
So the limitations kind of refer to the range of the quadcopters is only about 1 kilometer and really only used indoors. These are very light quadcopters, so any small gust of wind might really cause a perturbation that the quadcopter might not be able to recover from. And they only have 7 minutes of flight time on one charge, so that's probably the biggest limitation that we've run into so far. 15 minutes of charge for 7 minutes of flight time, you're not exactly looking at some of the most complicated trajectories that we could have.
So is there a time delay for the Vicon system?
There is a time delay for the Vicon system, but that hasn't seemed to be an issue yet. The biggest issue with the Vicon system is actually the calibration. So we calibrate the Vicon system using a special calibration wand, and from that calibration wand, we're then able to set like the origin of our system. And if that calibration is not good for whatever reason, or one of the cameras is shaken, for example, if the door to the lab opens and closes and shakes the walls because the cameras are mounted on the walls, then that will cause a bigger issue than any sort of time delay.